And number 5. Oh, my fault. Number 6. Elijah.
The box for an element from the periodic table is shown, which is the atom mass. That is D.
And number 7. About Amir.
The box for an element from the periodic table is shown, which is the atomic number. B.
And number 8. Jalen.
What happens to matter during a chemical reaction? I got A.
And number 9. Mari.
Which one is comprised of the other ingredients?
Number 10. Dylan.
76 grams sample of an unknown compound containing 12.9 grams of sulfur. What is the percentage of mass of sulfur in the compound? C.
Number 11. Matt.
How many electrons are in a neutral atom of sodium?
And number 12. Let's go with Nathan. 12.
No, I got that one.
Okay. 12. Vanna.
How many neutrons are in an atom of chlorine? A.
And 13. Let's go with Jacob.
What must occur for a change to be a chemical reaction? D.
And 14. Let's go with Nathan.
Which two have the same mass? It's D. Atoms assumed for.
15. Dylan.
The train travels at a speed of 30 miles per hour. 1 mile equals 1.6 kilometers. How fast does the train travel?
We know the charge of an electron based on Millikan's oil drop experiment. That's the goal today. The daily learning target is Millikan's apparatus. The students drew it in their notes, but we're trying to now help you understand where it is applicable. That is where it was used. I mean, he came up with the charge of an electron, but, you know, who cares? Well, the mole cares. That the mole is the number of particles or atoms or substances that you have in the mass. So we take a specific amount of silver nitrate. You need to know the stopping point for the silver. So you needed to know the weight, the atomic mass of silver. And if you look at Dalton's table, we were in the process of doing that, figuring out the masses for each element. Is everybody clear? So when you get to silver and you know its mass, then you can figure out how many atoms are in that mass by using the electron. If you know the charge of an electron and you're running a current, once you make that mass, which is 107, right? So when you make 107 grams of silver, you stop the charge and figure out how much charge you've used. So if you know the charge of a single electron, you can figure out how many electrons you gave to this silver here to make the silver. Does everybody see how we're using the electron to count the number of atoms in a substance? I know this is at the beginning of the book, but I have to talk to you about it here because when you get into the mole, they don't explain it there. They don't put the Millikan oil drop experiment there again. The mole isn't brought up again in the book until several chapters from now. But if I don't explain it to you now, you don't see it more than once, you're most likely going to forget it, that the electron was used to count the number you see behind you. The mole is the most significant number in chemistry. All of our solutions in chemistry, not to say all, but 99% are molar solutions. Sometimes you use percent solutions, but just not very often. The mole tells us how many we have, and that's very important to us. And it was counted based on what? Raise your hand. What do we use to count the mole? The electron. Now, it was verified with the diamond. Nice thing about a diamond, it has a crystal structure, and you can run light through it, and you can count atoms that way. It's a repetitive crystal structure. So we have double-checked this number, and it is valid. So it's actually pretty cool that Millikan was able to do this, and we were then able to count the number of atoms in a substance.
He discovered that electrons have negative charge. But he wasn't able to figure out how much negative charge electrons have, because charge is something that can come in different amounts. So scientists
in this apparatus, oil is sprayed into the chamber above the two parallel charged plates. The top plate has a small hole through which the oil drops. X-rays knock out electrons from the air particles between the plates, and the electrons stick to the droplets, giving them a negative charge. By varying the intensity of the electric field, Millikan could control the rate of the droplets' fall. He determined that the magnitude of the charge on each drop increased in discrete amounts and determined that the smallest common denominator was 1.602 times 10 to the negative 19th power coulombs. He identified this number as the charge of an electron. This charge was later equated to a single unit of negative charge, noted 1 dash. In other words, a single electron carries a charge of 1. So good was Millikan's experimental setup and technique that the charge he measured almost 100 years ago is within 1% of the currently accepted value. Mass of an electron. Knowing the electron's charge and using the known charge-to-mass ratio, Millikan could calculate the mass of an electron. The equation below shows how small the mass of an electron is.
All right, so I want you to draw this in your notes. This experiment has enormous implications for chemistry. It's probably one of the most important experiments ever done, because once you know the charge of an electron, you can start billing people for electric use. You know how much each electron charge has. So each little particle basically has a charge, and what that charge means, it has the ability to move something. So in this particular diagram, you're going to see how the charge was able to move the oil drop. And it's true today with electricity. When we talk about using electricity, like I'm using it right now, this microphone, it's allowing me to do work easier. So electricity allows us to do that. And you see like computers and typewriters and all sorts of other little gadgets that we have.
What did you say you're drawing?
You're going to draw the Millikan oil drop apparatus on page 109. Now, what is an atomizer? Anybody know what an atomizer is?
And it sprays it out like an atomic flow.
Right, turns it into a gas. So if you have an oil, it's very difficult to get an oil into a gas without an atomizer. You can throw it up in the air. I mean, it's going to try to evaporate. Oil just does not evaporate very well. It doesn't go into a vapor very well. So
force exactly equals the gravity force. The oil drop is just going to stay still. When this happens,
what's the protons? Remember we talked last week about a proton plus an electron equals a neutron, right? So if you're wondering how it's like suspending there, it's very difficult oftentimes for the atom to gain an electron unless it's in a solution or in water. Water has this ability, when we look at electroplating in liquids, to carry electrons easier. So in the atmosphere, as a field, it's not going to be as easy for the atom or this oil drop to pick up those electrons, and that's how it's going to be able to suspend there. The charge is, it's coming down, it's attracted to it. That is, it's attracted to the negative part of the magnet. Make sense? But it isn't actually neutralizing the oil drop. It's just hovering there in the middle, suspending.
drops of oil are losing charge in multiples of 160. So they think, aha, each electron must have 160 zeptocoulombs of charge. Because if you lose one, you have 160 plus charge. If you lose two of them, you have a plus charge of 320. So the drop that has this charge lost one electron. The drop that has this charge,
this is the pattern here they're trying to show you.
This one lost 3, this one lost 4, this one lost 5. That's where the positive charge is coming from.
So this one's going to take more to suspend. It lost more. It's going to take more of a charge. That's what you're seeing right here. You're seeing a greater charge. Does that make sense?
The oil drop apart is shown in figure 4.8. This is apparatus.
1, 2, in other words, a single electron carries a charge of 1.
negative. So good was Millikan's experimental setup and technique that the charge